para né, ouvir a palestra da Karen Garibaldi, da Universidade de Pisa, e ela vai falar hoje sobre a classic and new marine micropaleontological proxies, response from the late Holocene, benthic and planktonic communities of the Edisto Inlet in the Western Ross Sea, Antarctica. Okay, thank you. Welcome, Karen. You have the mic.
Thank you, Patricia. Thank you, everybody, for being here, and thanks to the ABECO organization for having invited me and for having given the opportunity to Vivian and I to take also Nkumari to your beautiful event. So, as said by Patricia, today I will talk about classical and new marine micropaleontological proxies. Don't expect me to conclude something at the end of this presentation. I will just give you some take-home messages, okay? And the reason why I'm willing to do that is because I am a micropaleontologist, I am a diatomist, and basically I often feel like I'm frustrated because a lot of my colleagues do have a lot of results in a short lack of time, or a short period of time. And me as a micropaleontologist, I'm always counting and taking a lot of time to get to my results. So let's start with the presentation. You may have understood that I will talk about something in Antarctica. You may be used to watch Antarctica from this side. This is West Antarctica on the west side and East Antarctica on the east side. But for what the Italian program for research in Antarctica, we used to look at the Antarctica from this point of view because we work a lot in what it's called the Ross Sea up here, okay? So the Edisto Inlet is a fjord that is located in the western Ross Sea, and it's related to East Antarctica. Why is the Ross Sea important? Why do we always study as Italian the Ross Sea? The reason is that the Ross Sea is very important. It is natural laboratory to study how the ice sheet reacts to climate variation. And it's also very important because in the Ross Sea, the Antarctic bottom waters are formed. And these are the waters that takes the nutrients, the waters filled with nutrients at low latitudes, okay? I would love you to focus on the fact that there is a quite warm current that flows from east to west, that is to say, the circumpolar deep waters. And these circumpolar deep waters enter the Ross Sea shelf when it's modified, and it's called, in that case, the modified circumpolar deep waters. You will understand later why I have made you focus on this current. So the Edisto Inlet, that we are going to focus on, is a fjord, as I said. It's more or less 15 kilometers long, and it's 4 kilometers wide. It has a main depth of 500 meters, and it's divided from the open ocean by a sill here, which is more or less 400 meters in depth, okay? So this sill divided from the open ocean. And the interesting thing about the Edisto Inlet is that not every summer it gets free from sea ice. As you can see here, this is summer of 2018. The inlet was completely free from ice, but every now and then it happens that it's closed, completely closed by ice, even during summer, okay? So as said before, it is important to study the Edisto Inlet for two main reasons. The first one is that, as I said before, it is related to the East Antarctica. So somehow studying the Edisto Inlet can tell us how the East Antarctica is behaving. And on the second reason is that sediment post-LGM, post-glacial maximum sediments have accumulated in this inlet with a sedimentation rate that goes from 0.7 to 0.2 centimeter per year, which is, you may understand, quite a huge sedimentation rate. So this allows us to make very high resolution studies in this inlet, okay? Indeed, this line here, it's the position of this core here, marine core, HLF 1701, which is one of the main cores that we are going to analyze. I will show you during this presentation three cores, TR178, HLF 1701, and GCE 003, which, as you can see, are aligned on a transect, a north-south transect inside the inlet, okay? And in particular, the third one, GC 003, is just in front of the mouth of a glacier. So all the cores were dated through carbonium-14, and as you can see, some of them span well beyond 2,000 years before present. You may know that the late Holocene, the last 2,000 years, have been studied a lot during the last decades, and the reason is that people says that you could see, studying the last 2,000 years, the effect on climate of the industrial revolution. Okay, so that's why it's so important to study them. So that's the core that I was talking about, HLF 1701. This is the core, it's 14 meters long. And what strikes your attention? What strikes your attention if you look at the core? Variation, yes. In particular, can hear? Lamination, exactly. It's completely laminated. It's made by dark and light lamina. So the first thing that we did in 2019, 2020, is study just one of these section, in particular section 3 of this core, from a micropaleontological point of view. And the reason why we selected this section is because the lamina are very thick, so there is less possibility to contaminate them while you are sampling them, okay? So if you want to sample one single lamina, because it's thick, you have less possibility to contaminate with another lamina just above or below it. And what are the results concerning these examinations? So it turns out that the dark laminae are mainly composed by this diatom here, which is Fragilariopsis curta, and the light lamina are quite monospecific and are composed by this other diatom, Corytrum pennatum. So the ecology of Fragilariopsis curta is related to the sea ice. That is to say that Fragilariopsis curta thrives in the marginal ice zone, okay? So it blooms when we have the first thaw of the ice, so the first melt of the sea ice at the beginning of the spring. On the other hand, Corytrum pennatum is a species of what we call the shade flora. What's the shade flora? The shade floras are a group of diatom species that do thrive at a high depth, around 200 meters in the water column. And they are called the shade flora because they can thrive at low light condition, okay? And indeed, they do thrive there at the thermocline, at the pycnocline, and they get advantages of the nutrients that are segregated under the thermocline. Probably, in this case, in the Edisto Inlet, Corytron blooms happens when we have the complete melting of the sea ice, and therefore a lot of input of fresh water that causes stratification, okay? So that's summer. We have Fragilariopsis curta in spring and Corytrum pennatum blooms in summer. And those two diatoms make different laminae, okay? Dark laminae, Fragilariopsis curta, light laminae, Corytrum pennatum. So that's the situation when Fragilariopsis curta blooms, a small opening of the sea ice, and a complete opening of the inlet when Corytrum pennatum blooms, okay? So beside beside this micropaleontological analysis, we made some geochemistry analysis on the laminae of section 3. And in particular, we measured ipso-25. Ipso-25 is an organic compound that is synthesized by sympagic diatoms. Sympagic diatoms are those diatoms that do live inside the ice, okay, at the bottom of the sea ice. Those yellow or green layer here are all sympagic diatoms, okay? So from this analysis, you can see that both ipso-25 and delta 13C are divided, the values are divided between light laminae and dark laminae. So the 0.42 nanograms per grams of opal ipso-25 divides light laminae from black laminae. So what did we do? Basically, the first author of this paper here translated all this information to the wall core, okay? So what he obtained are these graphs here, okay? This is the delta 13C for the wall core, and this is the ipso-25 for the wall core. And you can see here, these dotted lines are basically the threshold that we were speaking about before. So beyond this threshold, you have ice-free inlet, which are the gray squares here or rectangles here. And on the other side, you have periods when the inlet did not get free from ice during summer times, okay? So for example, this big rectangle here, this white rectangle here, is a long cold period that started more or less 700 years before present. And so it's a cold period, and as you can see, it does match with the record of the ice core in the Victoria Land coast. Okay, so the terrestrial record and the marine record do match together. However, these results have a couple of problems. The first problem is this one. The ipso-25 is meant to be, or is thought to be, let's say so, synthesized by this diatom here, Berkeleya adeliensis, which is this diatom here. As you can see, the photos are not that good, and the reason is that you do not have good photos of Berkeleya adeliensis in literature, and we did not make any photos because we didn't find it. So we find the ipso, but we did not find the diatom that is supposed to synthesize the ipso. So that's one first problem. Why is not Berkeleya adeliensis in core HLF 1701? The other problem is that with this analysis here, we have, let's say so, divided periods of cold period when you do not have the opening of the inlet during summer, and periods that do have the opening of the inlet during summer. But as you may understand, as you may imagine, the sea ice dynamics are much more complicated than that. Okay, you cannot resolve the history of this inlet just by saying, okay, there were periods when you did have a lot of sea ice during summer and period when you did not have. But those are the results of this first paper that we published in 2020. So one thing I forgot to say, the first core was retrieved in 2016. And this first paper came out in 2020. So you can see how much time it took us to publish the results. And you will see that it took us much more time even to publish the other results. So because we wanted to have a more detailed, let's say so, frame of what was going on in the Edisto Inlet during the last 2000 year or the late Holocene, we have implemented our micropaleontological analysis. And that's where my friend, let's say so, Giacomo Galli, comes out. He's a PhD student now, but he made his master thesis on core TR-17-8. And he studied the foraminifero assemblages there. So he started to take out some more information from this core thanks to the foraminifera analysis. So this is core TR-17-8. As you can see, it's all laminated, just as the other core that I showed you before. And Giacomo at first took into consideration only this section here, the top section from section 15 to section 9. And the reason why he did that is because these core, those sections match with the first 2000 year of the other core. So he basically wanted to compare HLF 17 with TR-17-8. And you can see indeed here, these are his results. It goes back to 2000 here. And he recognized different climatic phases thanks to the analysis of foraminifera. For example, at the very beginning at the bottom of the core, he recognized a seasonal phase. And how does he recognize it? So you can see that the fluxes of planktonic forams and benthic forams are quite high. I'm sorry. And also he found a lot of high energy species, basically Globocassidulina subglobosa and Globocassidulina biora. So these species are high energy species. What does it mean? It means that probably the connection between the inlet and the open ocean was open. So there were high energy current at the bottom, and that made Globocassidulina thrive. Then we have a transitional phase characterized by the lowering of the planktonic and benthic flux, and the increase of species like Steinfortia felingi and Milianina arenacea, which are typical of low oxygen content at the bottom. So probably at this point, at this transitional phase, the connection between the sea, between the ocean and the inlet was starting to close. That's why we had low oxygen at the bottom. And in the end, as you can see, in the end, he also found a cold phase, the same cold phase that was recognized thanks to IPSO 25, okay? And indeed, when the inlet is completely closed during the whole year, during this long period, we do not have any flux of benthic or planktonic foraminifera at the bottom. Also, Giacomo hypothesized that this first phase of the transitional phase do correspond to what we know as the medieval warm period or the medieval climate anomaly, as you prefer, and that this last cold phase corresponds to what we know as the Little Ice Age. Okay. So those are quite good results that were published by Giacomo in 2023, but he didn't stop here, because he found something very strange in this core. And now I'm going to ask you a question. What are these? Micropaleontologist, I want you. What? Patricia? No, it's not otolith, but in some way you are near. First I thought calcified butterflies, or maybe Egyptian statues, like this one, looks great. Any hypothesis? Well, because she told you. Oh, come on, that's not fair. Okay, micropaleontologists, do you know why you don't know them? Because they are not microfossils. Indeed, they are part of ophiuroids. So they are the skeletal elements of brittle stars, okay? So this brittle stars here, which is called Ophionotus victoriae, is quite well known by the Antarctic biologists, because it can like cover the sea bottom with mats of Ophionotus victoriae, indeed. And how is Ophionotus victorius made? How is his skeletal made? So a skeleton is made by a lot of different skeletal elements, okay? We have the proximal vertebrae that are the one that I show you. So they are the vertebrae of their arms, very close to the main body of the brittle stars. Then we can have dorsal armor plate, and then we have lateral armor plate, which are very important because they are the pieces of the skeleton that let you determine the species that you're looking at. And then we can have dental plate, okay? So another question, micropaleontologist or any other. If you would love to reconstruct the population of this Ophionotus victoria and have a statistical representative image of the population, what would you do? Any idea? Pardon? You have to what? Oh yeah, that's one thing. Okay. Yeah, that's indeed the correct answer. You have to cry because different skeletal elements can be representative of one single specimen. So it's impossible to estimate the size of the population, okay? You could have a lot of elements, and all these elements can be coming from just one specimen or from 10 specimens or from 100 specimens. You can never know, okay? So you know that when you are looking at foraminifera or diatoms, you have to count at least 300 specimens in order to have a representative image of the population, of your population. And you know that reaching 300 specimens, you have a statistical representation, good statistical representation of your population. But in this case, you cannot do it. So you cry. Exactly. Well, Giacomo, he made 1 year of physics, okay, before turning to a geologist, paleontologist. So he's very into statistics. And so what he tried to do to solve this problem is that he used presence absence data of this Ophionotus victoriae inside the core. So basically, he moved to the wall core now. He's studying the core until its bottom. And for each sample, he checked whether there were at least one skeletal element of Ophionotus victoriae. So he made basically a presence-absence matrix. So here you have 0. Those are all the samples which do not have Ophionotus victoriae. And here are the ones. So these are the samples that do have at least one skeletal element of Ophionotus victoriae. So at this point, he played a little bit with R, that you may know. It's a software that is used also for statistical analysis. And he applied to his matrix these JAM, generative additive models. There are models that are used to model the probability of occurrence over time, of occurrence in this case of Ophionotus victoriae. And you can see that these models can detect significant trends in temporal series. And in this case, you have a temporal series because the ages are your temporal series. So he applied this GAM to this matrix, and he obtained a curve of the probability of the occurrence of Ophionotus victoriae inside the core. And what it turns out is that there is a peak of the probability of occurrence of Ophionotus victoriae between 2000 years and 1500 years, which he called Ophioid optimum. And why is that important? It is important because we know quite well the ecology of Ophionotus victoriae. And we know that it needs primary production from the top of the water column in order to get to thrive and to get its nutrients, let's say so. So it is important for the CI cycle, for the yearly CI cycle, to be steady, let's say so. It's important for Ephrinotus victorius, a steadiness of the CI cycle. So in order for it to thrive, you need to have winters always covered by CIs and summers also always free by free ice. So it's a perfect proxy for the sea ice dynamics. And indeed, if you plot this interval here to the results, let's go back to the foraminifera results here, your ophiuroid optimum is here at the seasonal phase, okay? Corresponds to the seasonal phase. And indeed, when you look at the IPSO 25 values that comes from this core here, HLF 1701, you can see that these periods do correspond to the lower levels of IPSO 25. And because we know that IPSO 25 is made by sympagic diatom, this means that when you have low IPSO 25, you have low duration, shorter duration of the CIs, okay? So this match perfectly with the presence of the ophiuroid optimum here. So we have a great proxy for the CIs dynamics. And that's what Giacomo did. He published this paper in 2024. So once again, something that came almost 10 years after we retrieved the first core from the Edisto Inlet. But let's move forward, because I forgot to say, I told you that we have looked at diatoms, but I forgot to say that 90% of the sediment of this course are made by diatoms. So it would be a pity not to investigate the diatoms all along the core. And that's when my students, can I call her mine, Eleonora, came to play. She's a master's student. She should be get her degree next month, let's hope so. And she has investigated the diatom assemblage of HLF 17 for all along the core, not only in section 3. And he also investigated a little bit this core here that I remember you, it's just in front of a glacier, the mouth of a glacier. So I'm gonna show you just a few, not all, I'm not gonna comment on all the core, I just wanna focus you on some proxies, diatom proxy that we have been discussing about with Eleonora because are the most interesting to us. So this is the core, we saw it already. And those are Eleonora results. So I put a few species here, Fragileiropsis curta, Fragileiropsis cylindrus, Corytrum pennatum, and sorry, Proboscis inermis. And you can see the core goes down to 2,700 years. So I have plotted here the medieval warm period. And the first things that strikes your attention are those peaks of Proboscis inermis. Proboscis inermis is this diatom here, and surprise, surprise, she is part of the shade flora, so it thrives at the thermocline. But the other thing that strikes your attention is the fact that even Corytrum pennatum, as I told you before, is part of the shade flora, but it looks like it's behaving exactly at the opposite of Proboscis inermis. So what's going on here? So we don't know, basically. My guess is that there are at least two mechanisms that takes to the stratification of the water column. And because this is the medieval warm period, my guess is that this stratification here is given by some warm water entering the inlet, while for Corytrum pennatum, the mechanism was the melting and the release of fresh water. In this case, I would be extremely happy if I could say at the end that this Proboscis inermis is telling me that something warm is entering the inlet, and this warm thing could be the modified circumpolar the deep water that I was telling you when I introduced the oceanography of the Ross Sea. Let's move forward and let's go to the little ice age. So as we may have expected, Fragilariopsis curta is increasing a lot in the little ice age, because as I said before, it's typical of the marginal ice zone, so we are not surprised that it is increasing there. And also we have a drop in the abundance of choratron, because as I said, choratron is typical of free ice inlet, so we do not have free ice inlet in this period here. And what's more interesting is the fact that in correspondence of this ophiuroid optimum, something is happening even in the diatom record. And in particular, you can see here that there are some peaks. It's not very clear, so you may tell me, oh no, you are dreaming it, it's not there, but I see it. There are some peaks here of these Fragilariopsis cylindrus, okay? Fragilariopsis cylindrus is this diatom here, much smaller than Fragilariopsis curta, although it resembles it a little bit. But Fragilariopsis curta is defined as heteropolar because the two apexes are different one from the other, while Fragilariopsis cylindrus is called homopolar because the two apexes are the same, okay? And what's more important is the fact that they have the same ecology, okay? So they are both diatoms that do thrive at the marginal ice zone. And this thing, it's so true that sometimes if you get any, for example, I will suggest you Metzcheck and Tal 2017, I guess, you will see that this author plot Fragilariopsis curta and Fragilariopsis cylindrus together because they think that they are representing the same thing, the same ecological thing, okay? But look here. If you look at the little ice age, okay, you get this increase of Fragilariopsis curta and also a little bit of increase of Fragilariopsis cylindrus, which is what I would expect. But here, at the ophiuroid optimum, I do see these peaks of Fragilariopsis cylindrus, but you do not see an increase in Fragilariopsis curta. So what is happening here? Why are they not behaving as they should be behaving, like here? So if you look a little bit into literature, you will find this quite important paper from Armand et al. This paper is basically an ecological paper for polar diatoms. The authors basically have analyzed bottom surface, sea bottom surface samples. They have analyzed the diatoms inside there, and they have coupled the assemblages to the physical pattern, the physical, I cannot remember the name, well, temperature, salinity, and so on of the water above these samples. And as you can see here, this graph here represents the sea ice duration at different sites, okay? So this is the graph for Fragilariopsis curta, and this is the graph for Fragilariopsis cylindrus. And as you can see that there is a little bit of overlap between Fragilariopsis curta and Fragilariopsis cylindrus. So basically when the sea ice duration go from 7 to 10 months per year, they are there, they are both there. But when the sea ice duration drops and goes from 3 to 7 months per year, then you only have Fragilariopsis cylindrus. So that's the point. Here, we may not have an increase of Fragilariopsis curta together with the increase of Fragilariopsis cylindrus, because basically the sea ice duration was lower. And it does match with what the ophiuroid optimum is telling us, with what the IPSO 25 is telling us, okay? So we have a steadiness of the sea ice cycle with a shorter duration of the sea ice during the ophiuroid optimum. So that's something that we are about to write and see how it goes. And to conclude, as I told you, Eleonora is also looking at some another core here, the C003, and she's comparing what she's looking, what she saw in here with what she saw in HLF 1701. And as I told you before, the problem of this core here and also of this core here is that we have IPSO 25, but we do not have this guy here, Berkeleya deliensis. However, this core here does have at least two sympagic diatoms, which are Nicia stellata and Amphipora cuferati. The problem is that they have an abundance that is lower than 2.5% of the total assemblages. So normally you would not take, as a micropaleontologist, you would not take into consideration species that have an abundance which is lower than 3%. But in this case, comparing the two cores, knowing that this HLF 1701 has no diatom, no sympagic diatom, but those sympagic diatoms are here, then you start to think about the fact that maybe you should look better into those assemblages or into those species, even if their concentration is very, very low, because they may be, and that's what we are going to investigate, they may be indeed the producer of the IPSO 25. And the reason why they are in this core and not in this core is because this core is a little bit more inside the inlet, so it's where you get a lot more of CIs during the year, okay? And that's it. So my take-home messages, not conclusion, are this one. Micropaleontology is cool. So you may take a lot of time to study your samples, to count your diatoms, your nanofossil, your whatever, but don't be afraid, because you're gonna get a lot of great results and you're gonna impress all your colleagues. And do not stop at your first impression. Microfossil ecological data from literature are useful, but remember to interpret them, keeping an eye on what's going on in your research area. What do I mean here? Basically, if we didn't take a further look to the ecology of Fragilariopsis cylindrus and Fragilariopsis curta, if we didn't take a look into the duration of CI that they match to, we wouldn't have been able to resolve that problem there. So always be a little bit like a step beyond what normally the proxy is telling you, okay? And you never know what's worth counting. So as I just show you, sometimes even species that are below the 3% may be worth of notice, okay? And quality is better than quantity, okay? That's me telling myself, okay, Karen, you're doing great, don't worry. Although you're publishing not that much, but you're doing great. Take your time to do your research and to elaborate your results. They will tell you publish or perish. But science is not a competition. It's about doing the thing that you like in order to make the world better and increase your knowledge. I see someone nodding over there. Okay. And stress doesn't help. If you are always on an hurry to publish, you will not concentrate on your data and you will not be able to see what your data is telling you for real. So take your time and have fun. Thank you.
Well, thank you very much, Karen, for your beautiful presentation. Thank you. So, anybody has any questions for Karen? No. Oh, there's a question over there.
As I said, I'm not very much into statistics, but Giacomo is, so is doing that, yes. And they are recognizing some multi-decadal variation and also shorter variation, like I don't remember whether it was 8 or 18. We are discussing about them. We are discussing about the fact that the SEM may be influencing this variation in CIs. Yes, I mean, sun is always there. Exactly. And all these analyses, I mean, if you are interested, all these analyses have been run with R, and Giacomo can tell you which are the packages that he is using to do it.
Anybody else has any questions for Karen? I have something to say about your take-home messages, about looking at the samples, right? Okay, if you look at your samples, right, and they're very pretty, right, and but you don't find anything, right, at least you had this beautiful trip by looking at them, right? So I think you have to enjoy. I think the message is very important, because we think we have to give up when you have no data, or you think, oh, everybody's publishing and I'm not. No, I have data, believe me or not, 30 years ago, and I still publishing, right, Carla? So is there anybody else have any questions for her, or we're gonna just finish this? No, one more minute. Okay, I'm ready now. You. Oh, thank you, Karen. Thank you so much. Thank you. All right, so I think tonight we're gonna have a bus. So if you guys didn't pay yet to drink, not for free because you pay first, but then it's gonna be for free. Okay, so just go there, and I think it's at 8 o'clock. It's gonna leave our, the time of the bus that you guys are going to drink a lot. No, okay, but if in case anybody wants, go. Ciao, ciao. See you tomorrow. We have more, I guess.